Spring 1942. Bauxite, Arkansas. Steam hissed from mining equipment as aluminum ore thundered into rail cars bound for smelters across the Tennessee Valley. America's aircraft factories demanded metal, fast. Every engineering textbook said the same thing. Mass production destroys quality. Speed up smelting, you get impurities. Scale up mining, you get weaker aluminum. Accept compromises or fail to meet wartime quotas. European metallurgists had proven this for decades, but in a corporate boardroom that spring morning, a small group of American engineers proposed something that contradicted every rule of industrial wisdom. Use the purest Arkansas ore. Accept slower smelting cycles powered by abundant hydroelectricity. Prioritize aluminum durability over immediate tonnage. The room fell silent. It seemed impossible, choosing quality over speed during the greatest production emergency in American history. The aluminum they were about to create would outlast modern metal by over 40 years. The secret wasn't in how fast they could make it. The telegram arrived at Alcoa headquarters in Pittsburgh on December 8, 1941, just hours after the attack on Pearl Harbor. Aircraft manufacturers across America were doubling, then tripling their production estimates. Boeing needed aluminum for B-17 flying fortresses. Consolidated Aircraft required sheets for B-24 Liberators. North American Aviation demanded metal for P-51 Mustangs. The numbers were staggering. Not hundreds of aircraft, but thousands upon thousands, each requiring tons of lightweight, high-strength aluminum alloy. Arthur Davis stood in his corner office on the 40th floor, studying production reports that painted an impossible picture. Current American aluminum capacity stood at roughly 400,000 tons annually. The new wartime projections demanded over 2 million tons by 1944. Even accounting for every existing smelter running at maximum capacity, even factoring in recycled aluminum from civilian sources, the mathematics remained brutally simple. America lacked the raw materials to build the air force it needed. The problem traced back to bauxite, the reddish clay ore that served as aluminum's essential ingredient. For decades, Alcoa had relied primarily on imported bauxite from Dutch and British Guiana, supplemented by smaller European sources and limited domestic deposits. The company had pioneered the modern aluminum industry in 1888, when Charles Martin Hall's electrolytic process finally made large-scale aluminum production economically viable. The Hall-Héroult process, as metallurgists called it, required two key inputs: bauxite ore and massive amounts of electricity to power the smelting furnaces. But now, German U-boats prowled the Atlantic shipping lanes, threatening bauxite shipments from South America. European sources had vanished entirely under Nazi occupation. Davis walked to his wall map marked with red pins indicating aluminum facilities across North America. His finger traced the Tennessee River Valley, where Alcoa's massive smelters consumed electricity from newly constructed dams. Each smelter could process thousands of tons of ore monthly, but only if steady bauxite supplies continued flowing. The mathematics were unforgiving. It required roughly 4 tons of bauxite to produce 1 ton of aluminum metal. Meeting the military's demands would consume over 8 million tons of ore annually. 300 miles southwest in the hills of Saline County, Arkansas, lay deposits that could solve America's aluminum crisis, if anyone could figure out how to extract them efficiently. The town of Bauxite, Arkansas, had earned its name from the rich reddish ore discovered there in 1904. Geologists estimated the Arkansas deposits contained over 200 million tons of high-quality bauxite, more than enough to supply American aluminum production for decades. But in 1942, the infrastructure around those deposits remained primitive. Narrow-gauge railroads, outdated mining equipment, and a workforce measured in hundreds rather than thousands. George Brennan had spent the previous 6 months surveying the Arkansas deposits, taking ore samples back to Pittsburgh for analysis. What he discovered challenged every assumption about American bauxite quality. The Arkansas ore contained 60 to 70% aluminum oxide, comparable to the finest imported bauxite from South America. More importantly, it contained relatively low levels of silica, iron oxide, and other impurities that could compromise aluminum quality during smelting. Under microscopic examination, the Arkansas bauxite showed the uniform crystalline structure that metallurgists prized, the foundation for producing aluminum with consistent grain patterns and superior fatigue resistance. Yet conventional wisdom throughout the aluminum industry insisted that rapid scaling would inevitably compromise quality. European metallurgists, drawing from decades of experience with precision manufacturing, argued that mass production introduced too many variables: inconsistent ore quality, rushed smelting cycles, inadequate quality control. They pointed to examples from other industries where wartime production had sacrificed durability for speed, creating products that failed prematurely under stress. The technical challenges seemed overwhelming. Mining Arkansas bauxite at the required scale would demand constructing entirely new rail lines, expanding power infrastructure, and recruiting thousands of workers to remote mining camps. Smelting that ore into aircraft-grade aluminum required precise temperature control, carefully timed electrolytic cycles, and quality monitoring that traditional mass production methods couldn't accommodate. Most industry experts believed the choice was binary: produce aluminum quickly using existing methods and accept reduced quality, or maintain quality standards and fail to meet production quotas. But Brennan saw a third possibility, one that required abundant cheap electricity and a willingness to prioritize metallurgical precision over immediate tonnage. The Tennessee Valley Authority's new dams could provide nearly unlimited hydroelectric power at costs far below traditional sources. That cheap electricity made slower, more controlled smelting cycles economically viable, allowing time for impurities to separate, for aluminum crystals to form proper grain structures, and for each batch to achieve the purity levels that European craftsmen achieved through small-scale production. The stakes extended far beyond corporate profits or production statistics. Aircraft aluminum that failed under stress killed pilots, mechanics, and passengers. Fuselage panels that cracked from metal fatigue could cause catastrophic structural failure. Wing surfaces that corroded prematurely grounded aircraft when they were desperately needed. Every rivet, every sheet, every structural component carried the weight of American lives and the outcome of global war. By spring 1942, the decision could no longer be postponed. Aircraft manufacturers were placing orders that would commit Alcoa to specific production schedules and quality standards. The company faced a choice that would define American aluminum production for generations: embrace conventional mass production with its inevitable compromises, or attempt something unprecedented in industrial history. Martha Jenkins had lived in Saline County all her 34 years, watching the red earth reveal its secrets in cycles of boom and disappointment. Her father had worked the early bauxite claims when mining first came to Arkansas in 1904, hauling ore in mule-drawn carts to the narrow-gauge railroad that connected their remote hills to the outside world. By the 1920s, larger companies had arrived with steam shovels and more ambitious plans, but the Great Depression had shuttered most operations, leaving behind abandoned equipment and empty company housing scattered through the pine forests. Now, in early 1942, survey crews tramped across familiar ridgelines with instruments and notebooks, marking trees and driving stakes into ground that held some of the richest bauxite deposits on the North American continent. The ore lay in horizontal seams beneath 15 to 30 feet of overburden, clay, sand, and topsoil that would need removing before mining could begin. Geological surveys indicated continuous deposits stretching across thousands of acres, with ore quality that matched or exceeded the best imported bauxite from South America. George Brennan spent 3 weeks in Arkansas that spring, living in a boarding house in the town of Bauxite and walking the proposed mining sites each morning before dawn. He collected ore samples, methodically, marking each location with precise coordinates and recording detailed observations about soil conditions, drainage patterns, and accessibility for heavy equipment. Under laboratory analysis back in Pittsburgh, the Arkansas ore consistently showed aluminum oxide content between 62 and 71%, with low levels of reactive silica and iron compounds that could contaminate aluminum during smelting. But extracting that ore at wartime scale would require infrastructure that simply didn't exist. The existing railroad spur could handle perhaps 50 rail cars daily, enough for peacetime mining operations serving regional markets, but inadequate for feeding aluminum smelters across the Tennessee Valley. Meeting wartime production targets would demand moving over 15,000 tons of ore daily from Arkansas mines to distant smelters, requiring new rail lines, expanded loading facilities, and coordination with already overburdened freight networks. The workforce challenge seemed equally daunting. Current mining operations in Saline County employed fewer than 300 men, most working part-time or seasonal schedules that reflected the limited demand for bauxite in civilian markets. Wartime production would require thousands of miners working continuous shifts, along with support crews for equipment maintenance, transportation, and camp services. Finding experienced miners during wartime labor shortages meant recruiting from coal regions in Pennsylvania and West Virginia, copper districts in Montana and Arizona, and iron ore operations around the Great Lakes. Arthur Davis received preliminary cost estimates in late April that painted a sobering picture. Scaling Arkansas bauxite production to meet projected aluminum demands would require capital investments exceeding $50 million, new mining equipment, expanded rail infrastructure, worker housing, power lines, and processing facilities. The timeline was equally challenging, with full production needed within 18 months to meet aircraft manufacturing schedules that couldn't accommodate delays. More troubling were the technical concerns raised by Alcoa's senior metallurgists, men who had spent decades perfecting aluminum production using imported bauxite under controlled conditions. They argued that rapid scaling inevitably introduced quality variables that could compromise the final product. Hastily trained miners might mix ore grades, contaminating high-quality bauxite with inferior material. Rushed extraction could introduce dirt, clay, and organic matter that would carry through to smelting operations. Weather delays during Arkansas's humid summers might force wet ore into processing streams designed for dried material. The smelting implications were particularly worrying. Aluminum production required heating bauxite to over 1,000 degrees Celsius in the presence of sodium hydroxide, dissolving aluminum oxide while leaving impurities behind. Any contamination in the ore, excess silica, iron compounds, organic materials could create aluminum with unpredictable grain structures and reduced fatigue resistance. European metallurgists had documented cases where inferior raw materials produced aluminum that appeared acceptable during initial testing but failed catastrophically under prolonged stress cycling. Traditional quality control depended on small batches, careful monitoring, and the ability to reject substandard material without disrupting production schedules. Wartime aluminum production would involve continuous processing of enormous quantities, with little opportunity for detailed quality checking and virtually no tolerance for production interruptions. The mathematical reality was stark. Producing 2 million tons of aluminum annually meant processing over 8 million tons of bauxite, with quality control systems that could accommodate throughput rates 50 times larger than peacetime operations. Yet Brennan saw possibilities that his more conservative colleagues missed. The Arkansas ore's consistent quality across large deposits meant that proper extraction techniques could deliver remarkably uniform raw materials. The abundant forests surrounding the mining areas could provide timber for construction and fuel for steam equipment. Most importantly, the proximity to Tennessee Valley Authority hydroelectric plants offered access to cheap, reliable electricity that could support more energy-intensive but quality-focused processing methods. Local residents like Martha Jenkins understood the human logistics that would make or break such an ambitious undertaking. Housing thousands of workers in rural Arkansas meant building entire communities from scratch. Dormitories, dining halls, medical facilities, and recreational buildings that could maintain morale during grueling work schedules. The success of wartime mining would depend not just on equipment and engineering, but on creating stable communities that could attract and retain the skilled workforce that quality bauxite extraction demanded. By early summer 1942, the fundamental tension had crystallized. Arkansas held the ore that America needed in quantities that could supply aluminum production for decades. But extracting that ore at wartime scale, while maintaining the quality standards that aircraft safety required, would demand innovations in mining, transportation, and workforce management that had never been attempted in American industrial history. The conventional wisdom remained unchanged. Choose speed or choose quality, but don't expect to achieve both simultaneously. Lieutenant Colonel James Doolittle's raid on Tokyo in April 1942 had demonstrated American resolve, but it also revealed troubling realities about aircraft durability under combat conditions. Several of the North American B-25 Mitchell bombers experienced structural failures during the mission. Cracked fuselage panels, loose rivets, and aluminum fatigue that forced emergency landings in China rather than planned recoveries. Post-mission analysis traced many failures to aluminum inconsistencies in aircraft manufactured during the rapid production buildup of early 1942. The reports landed on Arthur Davis's desk, alongside similar documentation from European combat theaters. Royal Air Force maintenance crews reported premature aluminum corrosion in American-built aircraft operating from humid Pacific bases. Soviet pilots flying American Lend-Lease fighters noted wing skin failures that required extensive repairs after fewer flight hours than comparable aircraft built with pre-war materials. Each failure represented not just mechanical problems, but human lives at risk and American industrial credibility under international scrutiny. George Brennan studied these failure reports with the methodical attention of a metallurgist who understood that aluminum's microscopic structure determined its real-world performance. Aluminum alloy 2024, the standard for aircraft construction, achieved its strength through carefully controlled heat treatment that created precipitated copper particles within the aluminum matrix. When properly processed, these copper precipitates provided exceptional strength-to-weight ratios and predictable fatigue characteristics. But impurities in the base aluminum, excess iron, silicon, or organic compounds from contaminated bauxite disrupted the precipitation process and created weak spots that propagated into catastrophic cracks under cyclic loading. The mathematical reality was unforgiving. Aircraft aluminum experienced thousands of stress cycles during normal operations: pressurization and depressurization, thermal expansion and contraction, vibration from engines and turbulence. Each cycle created microscopic crack propagation that accumulated over time. High-quality aluminum with uniform grain structure could withstand these stresses for thousands of flight hours. Inferior aluminum with inconsistent metallurgy might fail after dozens of flights, often without warning signs that could alert maintenance crews. By summer 1942, aircraft manufacturers were reporting disturbing trends in their quality control data. Aluminum sheets produced during the initial production surge showed higher rejection rates for surface defects, dimensional inconsistencies, and mechanical property variations. Rivets manufactured from recycled aluminum exhibited premature loosening under vibration testing. Wing panels formed from mixed-source aluminum displayed unpredictable corrosion patterns that accelerated in salt air environments where many military aircraft operated. The pressure for increased production continued mounting regardless of quality concerns. Boeing's Seattle plants needed aluminum for B-17 production rates that had increased from 2 aircraft monthly in 1941 to over 16 daily by mid-1942. Consolidated aircraft required consistent aluminum deliveries to maintain B-24 production schedules that would eventually reach one bomber completed every 63 minutes. North American aviation demanded materials for P-51 Mustang production that would consume over 40,000 tons of aluminum sheets annually. Meeting these quotas using traditional approaches meant accepting compromises that experienced metallurgists knew would compromise long-term durability. Recycled aluminum, while abundant from civilian sources like cooking utensils and automotive parts, contained unknown contaminants that were difficult to remove completely during reprocessing. Mixed-grade bauxite from multiple sources created inconsistencies in ore composition that carried through to final aluminum products. Accelerated smelting cycles, designed to increase throughput, didn't allow sufficient time for impurities to separate properly or for aluminum crystals to form the uniform structures that provided optimal strength characteristics. Robert Hayes spent weeks that summer calculating electrical power requirements for different smelting approaches, comparing the energy costs of rapid production versus quality-focused processing. His analysis revealed a counterintuitive possibility. The Tennessee Valley Authority's abundant hydroelectric capacity could actually make slower, more energy-intensive smelting economically viable. While conventional wisdom assumed that longer processing times meant higher costs, cheap electricity from new TVA dams reversed that equation. Extended smelting cycles that consumed 50% more electrical energy per ton actually cost less than abbreviated cycles when electricity prices dropped below 2 mils per kilowatt hour. The engineering implications were profound. Longer smelting cycles allowed more complete separation of aluminum oxide from impurities, resulting in purer base metal for alloy production. Lower processing temperatures reduced thermal stress that could create microscopic defects in aluminum grain structure. More gradual cooling phases permitted aluminum crystals to form larger, more uniform patterns that provided superior fatigue resistance under cyclic loading conditions. Martha Jenkins observed the human dimension of these technical debates during meetings between corporate engineers and local mining supervisors throughout the summer. The miners understood ore quality in practical terms. They could distinguish high-grade bauxite from marginal material by color, texture, and weight characteristics developed through years of experience. Their concerns focused on maintaining consistent extraction techniques that could deliver uniform ore quality even during rapid scaling of mining operations. They knew that rushed mining, driven by production quotas, would inevitably mix ore grades and introduce contamination that would compromise the finals product. The culminating decision came during a 3-day meeting at Alcoa headquarters in late September 1942. Senior executives, production managers, and metallurgists gathered to resolve the fundamental strategic choice that would define American aluminum production for the remainder of the war and beyond. The meeting room walls displayed charts showing projected aircraft production schedules, maps of Arkansas bauxite deposits, and technical diagrams comparing different smelting approaches. Arthur Davis opened the meeting by summarizing the stark mathematics. Current aluminum capacity was insufficient for projected military demands. Foreign bauxite sources remained unreliable due to submarine warfare, and quality problems in rapid production aluminum were beginning to affect aircraft safety and American military credibility. The conventional solution involved maximizing throughput using existing methods, accepting quality compromises as unavoidable wartime necessities. George Brennan stood to present the alternative that his team had developed through months of technical analysis and field testing in Arkansas. Their proposal challenged fundamental assumptions about mass production, suggesting that America could achieve both quantity and quality through systematic application of abundant resources: high-purity Arkansas bauxite, unlimited TVA hydroelectric power, and precision-focused smelting techniques that prioritized metallurgical excellence over immediate tonnage. The room fell silent as the implications became clear. It could revolutionize American aluminum production, or fail catastrophically when the nation could least afford industrial experiments. The first steam shovels arrived in bauxite, Arkansas, on October 15, 1942, transported on reinforced flat-car trains that required temporary track modifications to handle the weight. Each Marion-type 91 shovel weighed 47 tons and could move 12 cubic yards of overburden per scoop, but their arrival marked only the beginning of the largest mining mobilization in Arkansas history. Within 6 weeks, Alcoa had positioned 18 steam shovels across 4 separate mining sites, supported by dragline excavators, bulldozers, and a fleet of Euclid dump trucks that could haul 25 tons of ore per load. Martha Jenkins coordinated the human logistics that made mechanized mining possible, but the scale dwarfed anything attempted in Arkansas mining history. The pre-war workforce of fewer than 300 men expanded to over 4,000 by Christmas 1942, with recruitment extending across the entire eastern United States. Coal miners from Pennsylvania and West Virginia brought experience with large-scale extraction techniques. Copper miners from Montana and Arizona understood the equipment maintenance requirements for continuous operations. Iron ore workers from Minnesota's Mesabi Range contributed knowledge about moving massive quantities of material on strict schedules that couldn't accommodate weather delays or equipment breakdowns. Housing this workforce required construction projects that transformed Saline County's rural landscape. Alcoa's engineers designed standardized barracks buildings that could accommodate 48 workers each, with communal dining halls, recreation buildings, and medical facilities arranged around central courtyards. By spring 1943, the company had completed over 120 residential buildings, creating instant communities with populations exceeding many established Arkansas towns. The largest camp, designated Site Alpha, housed nearly 2,000 workers and their families in structures that ranged from single-men dormitories to three-bedroom houses for married supervisors. The infrastructure challenges extended far beyond housing. Arkansas's existing electrical grid couldn't support the power demands of mechanized mining on this scale. Alcoa contracted with Arkansas Power and Light to construct dedicated transmission lines from generating stations in Little Rock, supplemented by diesel generators that could provide backup power during peak demand periods. Water systems required drilling artesian wells capable of supplying over 500,000 gallons daily for mining operations, equipment cooling, and residential needs in the expanded camps. Transportation bottlenecks threatened to limit production despite successful ore extraction. The existing Missouri Pacific Railroad spur could handle only 12 rail cars per hour, creating inevitable delays during peak shipping periods when mining operations produced over 800 tons of bauxite hourly. Alcoa's solution involved constructing parallel loading facilities that could accommodate longer trains while maintaining continuous ore movement from mining sites to rail yards. The company also negotiated priority shipping agreements that guaranteed aluminum ore, precedence over civilian freight on routes connecting Arkansas to Tennessee Valley smelters. George Brennan established quality control procedures that maintained ore consistency despite unprecedented extraction rates. Each mining site operated 3 shifts daily, with geologists sampling every 20th truckload to verify aluminum oxide content and monitor impurity levels. Ore with aluminum oxide content below 60% was segregated for separate processing or rejected entirely, ensuring that only premium-grade bauxite reached smelting facilities. This approach meant rejecting approximately 15% of extracted material, but it guaranteed consistent feedstock quality that would support precision smelting techniques. The mining techniques themselves required innovations that balanced speed with quality preservation. Rather than using conventional strip mining that mixed ore grades, Alcoa's engineers developed selective extraction methods that followed individual bauxite seams with minimal overburden contamination. Steam shovels worked in coordinated patterns that exposed ore deposits in horizontal benches, allowing visual inspection and grade separation before loading. This approach required more skilled equipment operators, but produced cleaner ore with fewer processing complications downstream. Weather presented constant challenges that threatened production schedules throughout Arkansas's humid climate. Summer thunderstorms could flood open pits within hours, requiring sophisticated drainage systems and pumping equipment capable of removing thousands of gallons per minute. Winter ice storms disrupted transportation and made equipment operation hazardous, forcing the development of heated maintenance facilities and all-weather operational procedures. Spring flooding along nearby creeks required constructing levees and diversion channels that protected mining sites from seasonal water damage. By summer 1943, the Arkansas operations achieved production rates that exceeded even Alcoa's optimistic projections. Daily ore extraction averaged over 18,000 tons across all mining sites, with peak days reaching 25,000 tons when weather and equipment conditions aligned favorably. This represented a 15-fold increase over pre-war Arkansas bauxite production, transforming a regional mining operation into the primary source of aluminum ore for American aircraft manufacturing. The human cost of this achievement became apparent in accident reports and medical records from the mining camps. Industrial accidents increased proportionally with production rates, despite safety programs that emphasized equipment training and hazard awareness. Heat exhaustion during Arkansas summers hospitalized dozens of workers monthly, particularly those recruited from cooler northern climates. Equipment maintenance crews worked 18-hour shifts to keep steam shovels and trucks operational, creating fatigue-related injuries that concerned both company officials and workers' families. Martha Jenkins documented the social transformation that accompanied industrial expansion, observing how traditional Arkansas communities adapted to sudden population influxes and round-the-clock industrial operations. Local merchants struggled to supply goods and services for thousands of new residents whose purchasing power far exceeded anything previously seen in rural Saline County. Schools operated double shifts to accommodate children from mining families, while medical facilities expanded to handle both industrial accidents and routine health care for the enlarged population. The success in Arkansas created new pressures throughout Alcoa's integrated production system. Smelting facilities in Tennessee received consistent deliveries of high-quality bauxite for the first time since the war began, but processing this ore at corresponding rates would require operational changes that challenged traditional aluminum manufacturing practices. The next phase would determine whether American metallurgy could match the quality achievements of Arkansas mining operations. The first trainload of Arkansas bauxite arrived at Alcoa's Alcoa, Tennessee smelting facility on November 3, 1942, carrying 800 tons of reddish ore in hopper cars that bore chalk markings indicating aluminum oxide content between 67 and 71%. Robert Hayes watched the unloading process from the plant's electrical control room, where banks of meters monitored power consumption across 48 individual electrolytic cells that would transform this raw ore into metallic aluminum through the Hall-Héroult process that had remained essentially unchanged since Charles Hall's original experiments in 1886. The fundamental chemistry was deceptively simple. Dissolve aluminum oxide in molten cryolite at temperatures exceeding 950 degrees Celsius, then pass direct current electricity through the mixture to separate pure aluminum from oxygen. But achieving industrial-scale production with consistent quality required precise control of dozens of variables that conventional smelting operations routinely compromised for speed. Each electrolytic cell consumed approximately 15,000 kilowatt-hours of electricity per ton of aluminum produced, making power costs the dominant factor in aluminum economics and the key to George Brennan's quality-focused approach. Hayes had spent months calculating optimal power distribution across Alcoa's Tennessee Valley operations, working with Tennessee Valley Authority engineers to coordinate electricity delivery from multiple dam sites along the Tennessee River system. The recently completed Chickamauga Dam could generate 108,000 kilowatts, while older facilities like Wilson Dam contributed an additional 630,000 kilowatts to the regional grid. Most importantly for aluminum production, this hydroelectric power costs less than 3 mils per kilowatt hour compared to 8 to 12 mils for coal-fired generation in other regions. This cost advantage created possibilities that European metallurgists had never seriously considered. Conventional smelting operations ran electrolytic cells at maximum current density to minimize capital costs and maximize throughput, typically completing each batch cycle in 36 to 48 hours. But higher current densities generated more heat, created turbulence in the molten electrolyte, and reduced the time available for impurities to separate properly. The result was aluminum with acceptable purity for many applications, but suboptimal grain structure and higher concentrations of iron, silicon, and other elements that could compromise long-term durability. Brennan's alternative approach extended electrolytic cycles to 72 or even 96 hours, using lower current, densities that consume 20 to 30% more electricity per ton but produce dramatically purer aluminum. The longer cycles allowed aluminum oxide to dissolve more completely in the cryolite bath, reducing undissolved particles that could become impurity inclusions in the final metal. Lower current densities minimized electromagnetic stirring that could trap gas bubbles or foreign matter within solidifying aluminum. Most critically, extended processing time permitted thorough separation of aluminum from residual compounds that rapid smelting left behind. The metallurgical benefits became apparent immediately when Alcoa's laboratories analyzed the first aluminum produced using Arkansas bauxite and extended smelting cycles. Spectrographic analysis showed aluminum purity exceeding 99.8%, with iron content below 0.05% and silicon content below 0.03%. These impurity levels matched or exceeded the purest aluminum that European producers achieved through small batch processing, but Alcoa was generating these results at industrial scale with production rates exceeding 100 tons daily per smelting facility. Temperature control proved crucial for maintaining quality during extended processing cycles. Hayes installed sophisticated pyrometric systems that monitored electrolyte temperature within 5 degrees Celsius throughout each batch cycle. Maintaining optimal temperatures required coordinating electrical input with heat dissipation, using water-cooled copper conductors and ceramic insulators that could withstand thermal cycling without developing cracks that might contaminate the aluminum bath. The investment in temperature control equipment added significantly to capital costs, but it enabled precise metallurgical control that traditional smelting methods couldn't achieve. The extended smelting cycles also permitted innovations in aluminum grain structure that would prove critical for aircraft applications. Conventional rapid smelting produced aluminum with relatively small, irregular crystal grains that provided adequate strength but limited fatigue resistance under cyclic loading. Slower cooling during extended processing allowed aluminum crystals to form larger, more uniform grain patterns that distributed stress more evenly and resisted crack propagation more effectively. Laboratory testing showed that this improved grain structure increased fatigue life by 40 to 60% compared to conventionally processed aluminum. Quality control during the smelting process required continuous monitoring that challenged traditional production management approaches. Each electrolytic cell operated as an individual batch processor with slightly different thermal characteristics and power consumption patterns that could affect final aluminum quality. Hayes developed detailed record-keeping systems that tracked temperature profiles, current density variations, and processing times for each cell, creating databases that permitted optimization of operating parameters based on empirical results rather than theoretical calculations. The human element remained critical despite increasing mechanization of smelting operations. Experienced smelter operators could detect subtle changes in electrolyte behavior, variations in surface appearance, unusual electromagnetic humming, or temperature anomalies that preceded quality problems or equipment failures. Training operators for quality-focused smelting required different skills than conventional high-throughput operations, emphasizing patience, attention to detail, and willingness to interrupt production cycles when conditions weren't optimal for quality aluminum production. By spring 1943, Alcoa's Tennessee Valley smelters were producing aluminum that exceeded aircraft industry specifications for purity, consistency, and mechanical properties. Laboratory tests showed ultimate tensile strength averaging 45,000 pounds per square inch for pure aluminum, compared to 38 to 42,000 psi for conventionally smelted material. More importantly, the improved aluminum showed superior performance in fatigue testing that simulated thousands of stress cycles typical of aircraft operations. The success created new challenges as aircraft manufacturers requested increasingly large quantities of this premium aluminum for critical applications. Boeing specified Alcoa's Tennessee Valley aluminum for B-29 Superfortress production, recognizing that the aircraft's high-altitude pressurization requirements demanded materials with exceptional fatigue resistance. North American Aviation requested similar materials for P-51 Mustang production, particularly for wing structures that would experience severe stress during high-speed maneuvering. Meeting these demands while maintaining quality standards would require the next phase of Brennan's integrated approach, transforming pure aluminum into aircraft-grade alloys without compromising the metallurgical advantages achieved through careful smelting.